So picture this. You've got 3 absolutely perfect, totally indestructible security locks. You've tested them all individually and they are flawless. But what happens when all 3 of those locks try to secure the exact same door at the exact same time with completely different instructions? Well, if you aren't careful, you might just build an impenetrable fortress that accidentally locks you out of your own smart contract. No way you want that, right? Welcome to the Foundry by Forge College. Let's jump right into this explainer, where we're going to dive really deep into the conceptual architecture of smart contract security, specifically looking at the integration design review. Now, as you move through the applied Solidity development track, and specifically the capstone for the AccessControl patterns course, you hit this critical milestone. You've built all the brilliant individual security pieces, but before we write a single line of integrated code, we absolutely have to confirm our design choices. Okay, here's our agenda for today. First up, the hallway of gates. Then, mapping your guards. Third, the integration workflow. Fourth, balancing contract trade-offs. And finally, the final blueprint. Let's get to it. Section 1, the hallway of gates. So in the last lesson, you built some seriously solid isolated security doors. But to secure the whole building, we need a cohesive mental model. We call this the layered gates metaphor. Basically, it's a framework that treats access control as an ordered sequence of physical barriers down a hallway, rather than just throwing a random handful of independent modifiers onto a function. The absolutely crucial point here is that authorization must be an ordered sequence of checks. If you treat them as totally independent, they're going to conflict, and trust me, someone is going to get stuck in that hallway. Let's break down how this actually works with standard components. Think of Ownable as your master entrance lock. It handles the big stuff, contract-level ownership. Then AccessControl acts like the interior room doors, giving you that fine-grained role privilege. And Pausable? Well, that's your emergency shutoff for a global incident response. When you look at it this way, the logic just clicks. I mean, you wouldn't trigger a building-wide fire alarm just to open a broom closet, right? Each gate serves a very specific threat model. Section 2, mapping your guards. This brings us to rule number 1 of integration. Your function to guard mapping has to be the single, absolute source of truth before you finalize the implementation. Seriously, before you type any code, you need a crystal clear list detailing every externally callable function and the exact modifiers and internal checks it's going to use. Notice the exact evaluation order we require here. If a user calls a function, your contract needs to consult this specific sequence. First, is there a global emergency state? If it's paused, reject it immediately. Next, check the contract-level ownership constraints. Then, verify the role-based privileges. And finally, check the function-specific predicates. This order, it's non-negotiable. An emergency gate, like a pause, has to short-circuit your standard role checks to halt all non-essential behavior during an incident. Section 3, the integration workflow. Here at Forge College, structured workflows like this are an absolute staple. Why? Because they turn abstract design ideas into hard, executable safety checks. Let's walk through this 5-step workflow like we're looking at a procedural engineering manual. Step 1, like we just talked about, map your functions to guards. Step 2, verify state compatibility. You've got to confirm that storage variables like your pause flag and role mappings don't clash. Step 3, check your initialization semantics. Who is calling the initializers and in what order? Step 4, document your modifier rules. And step 5, convert the whole shebang into verification tests. Now, I need to pause here for a second to issue a major warning. Beware the upgrade collisions. If you're planning to make the system upgradable, you absolutely have to ensure your storage slots and initializers are strictly deterministic. A super common and honestly really subtle integration bug happens when an ownership flag goes uninitialized or maybe a pause flag becomes totally unreachable after a proxy upgrade simply because the storage slots didn't align perfectly. It is a total nightmare. Section 4, balancing contract trade-offs. Look, every time you bolt another security gate onto your hallway, you're increasing 2 things, gas costs and cognitive overhead. It's a deliberate compromise. If you want high granularity with really precise role permissions, the cost is a higher per-call gas fee because of the extra storage reads. If you want a flexible emergency recovery, well, you're increasing your contract's complexity and expanding the attack surface. And if you want upgradability, you're sacrificing some layout clarity because you need strict storage alignment. One of the most critical tugs of war you'll have to navigate is single authority simplicity versus distributed governance. Let's be real. A single owner can act with incredible speed during an emergency, which is awesome, but it heavily concentrates your risk. On the flip side, distributed role-based governance reduces the risk of a single key compromise, but it requires consensus, and consensus is slow. You have to explicitly decide which of these methods governs your most critical recovery functions. Which brings us right back to our golden rule of mitigation. Say it with me. Evaluate authorization as an ordered sequence, not independent checks. Establishing a strict sequence and thoroughly documenting those override flows are literally the only ways to prevent conflicting authorities from completely tearing your protocol apart during a crisis. Section 5, the final blueprint. All right, here are the concrete design artifacts you absolutely must have on hand before jumping into implementation. Use explicit revert messages on all your guards, because generic errors will just make your testing a total nightmare. Prefer named bytes32 constants for your roles. This stops silly typos and actually saves valuable gas on hot paths. Group infrequently used functions under higher privilege gates to minimize your overhead. And always replay your initialization sequences in your test suites to catch any missing assignments. Ultimately, your blueprint is completely useless if it isn't tested. You need to convert every single manual design check into an automated verification test. Make sure every explicit revert message is mapped out and verified before you even think about hitting deploy. Testing is the magic that turns your design intent into verifiable reality. Complex systems are inherently fragile, and as you layer all these security gates, it's so easy for blind spots to form. So I want to leave you with a provocative question to ponder before you write that first line of code. What hidden backdoor did you accidentally engineer into your own integrated protocol by failing to check the overlap? Think very carefully about your gate sequence. Well, I really hope this explainer gave you a clear, solid roadmap to secure your capstone. Don't forget to head over to forge.college to learn more about this subject, explore deeper Web3 concepts, and check out all our other amazing learning resources. Keep building safely, and I'll catch you in the next explainer.